Hello, everybody. Let's wait a few more minutes to have more students join our live solutions. If you are a current SCAM student of bronze level, feel free to leave any question about this contest. Stacy is our teaching lead and bronze level coach. So welcome everybody to join our bronze level live solution. After this bronze level ends, we will host the silver level on the same Zoom. So if you are choose the gold level, there's another Zoom link. I would copy in the chat. Stacy.
现在开始。
Okay, sure. Yeah, let's get started. Yeah, I will hand over to Stacy.
Let's wait a sec for me to airdrop the question to my iPad. Uh, I will alter between my iPad and also my computer. When I'm going over the problem, I'll be using the share screen from my PC. But if I'm teaching for the true solution, I will be using my iPad. So here's the first questions. It's called make all distinct. You're given an integer exactly in the range from 1 to n to the magnitude of 2 to the 10 to the power of 5 as non-zero integers. And some of them might be overlapping. For those overlapping number, you got the operation allowed to move them k distance away from its original places. The input you will be given t test cases, and you will be only given 1k. That is, you're only allowed to move this k if the k is positive, then you're allowed to move it to the right. If k is negative, then you're allowed to move the collision number. And it's guaranteed that the sum of n over all test cases do not exceed 10 to the power of 6. I'm going to switch to my iPad for further walkthrough of this problem. So here are some of my observations for this problem. If you can see my screen clearly, I noticed that for any number, they can only move by k. So either if the k is positive, then if any two collision number happen on the number line, you can only walk k distance, step size of k. So if k is greater than 0, you can move k or double k. So it's only taking a step size of k. So if k, on the other hand, is negative, then when a collision happen, all you can do is move your point left to a step size of k. So the remainder does not change because for any number within the number line, you can basically represent it by using AI times k plus a remainder. So for any number within this given 1 to n, you can decompose it. Let's say this number is pi. You can decompose it into some multiply of k plus some remainder. if we represent every integer number in this range in this form, you will notice the allowed operation only allows it to move to, let's say, AI plus 1k plus ri. This is when you take one step. If you take two steps, this pi has become AI plus 2 times k plus the remainder. So I have noticed the remainder does not change. So when we're moving, whenever there is a collision happening in this range, I can choose to move the collision point k steps away, and the remainder does not change. So I should only be careful. The only thing I'm concerned about is after moving, let's say I'm down k step, I moved one operation. However, there is another number occupying my future moved 2 points. So my future definition. This is the only thing I'm afraid of. That is, I moved my number, but there is a collision in the future. So I have decided since the next point I move to will have the same remainder as me, I have decided to partition the number according to the remainders. Um, so as I notice, if there's a collision happen, I decide to move to the nearest untaken points. But the untaken points must have the same remainder as me. So I have decided let's sort the number from the smallest to the largest. This is when k is greater than 0, I decide to sort the number from smallest to largest. And I partition them into k groups. Because the k's are the possible remainders. The possible remainders you can have is going from 0 to k minus 1. I decided to partition the number into k groups. So for the k groups, some of the number may fall into the remainder group 0. So that means it's completely divide k. So some numbers fall into the group of remainder 0. Some of the number fall into the group of I have a remainder of 3. But why does this matter? Because first of all, I have sorted numbers. The number, if k is greater than 0, then I sort the number from smallest to the largest. Then I know the numbers are strictly increasing. So for every number, I'm going to try to assign it to the partition remainder groups. And in the remainder groups, you will notice if there are collision happen because in the remainder group, I no longer store the number itself. I store the number floor divided by k. That means how many multiply of k does this number represent? So if two numbers, they actually reside in the same remainder group, and also their floor division is the same, that means there is a collision. Then I try to move to the next untaken spot within the same group for this collision number. That's basically the idea for this solution, and I'm going to give out a code planning for this code. So this is my code structure planning. I have T test cases, so I read in T. Now for each test cases, you will have this N and you will have K. Now I want to group the remainder by I want to group the number by remainder. So I will use a map data structure to stop the remainder and map to all the list of values that have the same remainder. So basically all I do is this is my remainder, and then I append the number to this group. So I have my map, which is just like the visualization I presented before, you have the number. The only differences between k greater than 0, k smaller than 0 is for k greater than 0, then I will sort my number in ascending order. So I'm going to assign the number from smallest to largest. This is to avoid some number, if you're given the number in random order and you're trying to assign them, along the way, along the fly, you might be taken the future position where the future patient position supposedly is going to be having another input number. So the best way to save your steps is to actually sort them ascendingly and assign the number one by one beforehand. So you know the next number is going to be for sure greater than the previous one. Either it's going to be in a different partition remainder group, or it's going to be taking a larger spot compared to your previous assigned number in the same remainder group. So this is a controlled and ordered way of assigning spots and resolving the collisions. At the beginning, the previous I assigned it to negative infinity because within the remainder group, none of the number has been assigned value yet. Let's give an example. So my n, it's I have, let's say, 10 numbers. My k is equal to 3. So let's take a look at one example I have created. Then for a sorted input, then you have 3, 9, 7, 12, 12, 15, 15, 15, 18. So you will have two groups, basically a remainder that is 0 and then a remainder of 1 for this 7. So I have partitioned them into remainder groups. This is sorted in ascending order group. Now for this 3, if you 4 divided by 3, it's 1. So that means 1 is taken, a multiply of 1 plus the remainder 0 is taken. Now this 9 comes, that means 3 is taken. 3 times 3, it's 9. Now when this 7 comes for the remainder 1, you know 2 is taken. Now when this 12 comes, you know 4 is taken. What's interesting is when this 12 come, I know 4 is already taken. So I need to find the next immediate spot greater than the previous 4. So I can move this collision 12 to the next available point, which is 5. Now for this fly, how many steps or how many operations I have added a k to? I added 1k because basically this means I move this 12 to 15. Now, when this next 15 tells, if there is no previous 12 that's taking its supposed like spot in this partition group, I should have put this 15 in the spot of 5. But however, since this 5 is taken, I should go and find the nearest spot who can represent this 15. Basically, this 15 is going to take the spot for 6. So I'm using 18 to this 15. Now how many steps I have moved this 15? I moved one spot to the right. I used the operation one time. Now when another 15 comes, again, since its spot is longly taken, if there's no collision, it should be at the spot 5, but all the two nearest future spot have been taken, then this 15 is put in the spot of 7, and it have made two operations. So you can do this along the way and find this 15 is taking the spot for 8, and it moves 3 operation. And this 18, if there's no collision, it should be at 6. But the nearest spot I can put it is at 8. Basically, I'm using 27 to represent this 18. Now the step I have taken is 3. Now the total operations I do to resolve the collision is actually 10. Basically, this code is doing this process. How is it doing though? For each value, that is for each value, for each number in this group, so I ask for my x, what is my current assigned value of this number? If the current assigned number should be greater because I have sorted the number in ascending order within the group. If it's actually greater, that means great, no collision happened. So I should move on to the next number. So I update my priv to be my current x. In the else cases, that is, oh, there is a collision happen because either someone else taken my point, or I'm in the case where the priv is equal to x. Two numbers are the same. or there was a collision happen like this 20. Um, this 20 is, oh, someone has taken my spot. So when it's 12 mid, the priv is going to be equal to x. So you're assigning the same number again. Or it's in the case where this 12 and 15 happened. This 12 basically is assigned to 21. And this 15 is now smaller than the 21 because it knows all the previous spot has been taken. So I should seek for future spot to represent this 15. So I ask for like how many distance I should travel and divided by the step size k I should be taken. Since the priv and x, they should not be overlapping. I should add 1 to it to avoid overlapping between priv and x. So this is, imagine priv and x are the same, then 0 divided by the step size k means you need to move them 0 step. However, that's not the case. When priv and v are the same, that means you are given two exact same numbers. So you need to move at least 1 step. That's what the +1 is here for. And the only differences between k greater than 0 and k smaller than 0 is you should store your number in descending order when k is less than 0, since everything is moved to the left. Now, when you have actually find out the steps, then you update the steps, and then you should updating what the spot that has been taken by your previous number, because now they have the collision and this is a number of steps. You have decided to move the previous number, and now this priv is the final last number you have resolved the collision into. For example, when you resolve this collision for 12, you have actually represented not by 12 but by 15. I want to stop here for any questions. You can open your microphone or type in the chat for questions. Okay, if not, I will move on to the second question. The second question is called strange functions. Basically, you have designed a function that has two operations. So branch one is if x is your input number. And according to the problem statement, I think x is really large. X is to, let me see, 10 to the 2 to the power of 10 to the power of 5. Something that is really big. We can barely represent it by long. So it offers that we should multiply the number. Let me check again. Yeah, it's 10 to the x is 10 to the power of 2 times 10 to the power of 5. So it's a really large number, and it's hard to imagine. So basically, this number tells us you should not brute force to simulate. This is telling you do not simulate because the simulation takes forever. The size of the x already discourage you from attempting it. It says the x, you will be given like a random number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a random number. So we would observe this number. If x has any digit outside of binary 0 and 1, if this you will replace each digit from the odd number, you will set it to 1 if it's odd. You will set it to 0 if this number is even, and then return the result. So basically, you update the x accordingly. Otherwise, if the x is already a binary number, you will just do -1 to x. Since x is really large, we should replace every answer here, the application, to mod this 10 to the power of 9 plus 7. So in my observation, I find for any number in the case one, it will transform the number into a binary number. So doesn't matter what x was originally, depending on if it's even or not, you will replace the number into 1 and 0. So basically, it will make it into a binary number. Now, once this number has become a binary number, there are two cases. If it's actually ending with 1, you will do -1. So you will see this arrow I draw. If this number is a binary number, if it's 1, you -1, it becomes a binary number ending with 0. And now this is a binary number ending with 0. You should further do -1 to it. So the last number, doesn't matter what the previous number is, the last digit actually become 9. This 9, again, let's go back to branch 1. There is a digit that is outside of 0 and 1. Now this is surely an odd number, so you will make this into a 1 again. And now this one will do x minus 1 again, and it goes to the cycle of 0. So I noticed there is an infinite cycle in case 2, and I know it's a binary number anyway. So I want to try to see what pattern I can find in transforming some binary numbers into 0 as it's required. So I represented out some binary number. Here are some binary number I tried. I go from the smallest binary number, which is 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So on the left-hand side is their binary representation. In the middle is the actual number. And finally, it's the actual steps I have tried out to make it into a 0. So for this 0, it's already 0, so there's 0 step needed to make them into 0. Now for the binary number 0 and 1, and all I do is just -1. Go into branches 2, and that made, so the binary number, if it's 0 and 1, then I applied branch 2 to make it 0, 0. And I know I have taken one step. And now for the binary number 1, 0, the numerical value represented is 2. Now it follows into branch 2, I do -1. So this 1, 0 actually become 9. And now since this is an odd number, I replace this digit with 1. And now this 1, it's follows in the branch 2, I do -1, it becomes 0 again. So I notice it's 3 steps. So, and I follow this pattern. Now I go to 1, 1. So for this binary 1, 1, it's an odd number. So I go ahead and replace the digit with like, it's binary and it's odd. So I do -1. It becomes 1, 0. Surely I notice, oh, I have done operation for 1, 0 before. And 1, 0 takes 3 steps to become 0. And it takes me only 1 additional steps to go from 11 to 10. So I know the total steps is 4 without any doing this like the actual computation. I realize this 10 actually I pre-computed it, or depending on the previous answer here, I can use this answer directly. And I notice this pattern again at the binary number 1, 0, 0. So for 1, 0, 0, I used x minus 1, it becomes 99. And I applied this branch 1 again, it becomes 11. And then I noticed, oh, this 11 has been calculated before. I can rely on the previous steps 4 and add to it, 2 to it, and to get 6. And then I realized this pattern again and again. As you see, this 100, I can easily turn 101 into a 100, and this 100 is pre-calculated before. So I have noticed there is a dependency going on. It's like a recursion. I surely noticed if the binary number it's like if the binary number numerical value it's odd, then the steps is just +1. I noticed if the binary representation numerical value is even, then it's just +2 from the previous steps. So we can actually confirm it. This is 3, so you know there is a +1. 3 plus 1 to get 4. Now this 4 is even, it's +2. 4 plus 2 is 6. So I can follow this pattern easily to generate all the steps needed for any binary numbers. So from this pattern, I can surely conclude, wait. So from this pattern, I can safely tell myself all number that is in binary form, I can find the operations needed. Now the problem can be condensed easily. So if I'm solving this on paper, I would say first reading x and then set the count to be 0. I've done nothing. Now if any of the digit x is not in, so if x not binary, you will use the branch 1 to make it into binary. So count plus plus and make it into binary. And now, since x is in the 0 and 1 digit form, um, x is now binary. There is going to be some special cases where you are really lucky after in branch 1, the x already turns into a bunch of 0. So you should check for these special cases. When x is already 0, then the steps is just 1. Otherwise, if this x in binary form is not 0, um, you will transform the binary number into a numerical value. Because even though, well, you can use recursion, basically, f0 is equal to 1, f1, f0, which is numerical value 0, it takes 0 steps. F1, it's on, it takes 1 steps. And then you can basically say fi, if I is even, then is fi minus 1 plus 2. If I is odd, then you can do fi minus 1 plus 1. However, if you know recursion, this is still a open solution. And x here is really big. X here is 10 to the 2 to the 10 to the power 5. So it's quite impossible for us to actually go over this binary search and over this binary numbers and digit to actually rely on x numerical value. But we're actually not using x numerical value. We're using x digits representing the binary number. So how many digits can this x have is log 2 to the maximum of x can be is maximum 2 to the 10 to the power 15. This is handleable. So we can actually compute step-by-step processing this number in binary number digit by digit and get the answer. So let's interpret. So transform the number. So we can actually, so the idea of transforming the binary number back into numerical value is not actually feasible. So we should be interpreting the digital string as a binary number b. And then if we actually observe this pattern, you will find if this is the numerical value b, then the steps can be represented by 3 times b4 divided by 2. And then you take a floor into that. So there is a O1 solution to find exactly how many transformations are needed, depending on like what's the numerical value for b. So for step 5, so we can greatly compute 3b floor by 2 and mod, since the steps should be mod by 10 to the power 9 plus 7, and then add to the step. Using this result, we add to the count and output the result. There is one thing I want to talk about in the implementation. Um, so basically here you want this 3b divided by 2 to mod this 10i plus 7. This b, the binary representation's actual numerical value is going to be very large. So no container is going to safely hold 3 times b. So here is my, in my code I did, so this is my mod value. So 10 to the power of 9 plus 7. This is exactly what I did in my code. This is a pseudocode I'm going to go over. So this is the steps I actually avoid calculating the speed. This is a classic measurement for transforming a binary representation back to the numerical value, but bound the numerical value within the 0 to mod, within the basically the mod limit. I'm going to explain shortly how you avoid kind of generating a really large number along the way. Um, so here you reading this x as a string, that is our initial data, and you go into branch 1. You check for if any of the digits not 0 and 1. Um, so the initial count is 0. So if the number is already binary, then you go into the step B directly. However, if the number is not binary, so you need actually phrase 1 to transform into binary. So the count is initiate to be 0. And then you basically change the number into binary according to its rule of whether it's odd or even. Um, Now my step B is the special cases when after one step of transforming it into binary number, this number already becomes 0. So you should be removing the leading 0 from x because they contribute nothing. And then if this x, after removing the leading zeros, it's already 0, then that means using one step, we already make it into um, a 0. Now it's in step C, so that's what we conclude. 3b 4 by 2 is actually the number of operation needed. However, b itself is really large, so we need to construct the binary number from the last digit back to the original number, but we need to constrain it within b mod is 10 to the power of 9. Basically, it's b mod mod. So mod here is defined. Um, if you remember how we transform the binary number back to the original number, is we always go from the last digit. And so for example, 111, we go from the last digit. The last digit is 1. 1 times 2 plus 1. Then this is 3. Basically, 1 is representing 3. And then to represent 111, you time this again, 2 times 3 plus 1. So it's 7. So you always do this b mod times 2 plus whether or not the last digit you are actually inputting is 1 or not. And then to make this big, really, really large B into the boundary where the question asks for within this mod bound, every time you do times 2 and then plus the last digit, you should always mod them by the mod. Um, so you always get the last digit, and then starting from the last digit, you rebuild this B, and then every time to avoid overflowing beyond the mod, you mod. And now finally is once you compute this B within this mod sign, you use the 3b divided by 2. All this is just following mathematical transformation for the mod calculation. And this is how I solve this problem. Any question here? If not, let's go into the last questions. I think the last question is the most fun one. Oh, I see there is a question in the chat. Um, so the last question is called swap to win. You're given a letter matrix. So you have a target string and an helper string from S1 to Sn. Um, I assume you already read the problem statement from S1 to Sn. It's a letter matrix because S1 can have letters going from 1 to N. So it can have, let's say, banana in the sample statement. So you will have a letter matrix. And you are allowed two operations. You have a target string. Let's say T, that's of the same size as is also of M letters. And you're only allowed two operations. So either you are allowed to find two target positions within a string. So I can find two target position within the string and do a horizontal swap. Or I can find two vertical places within the string, within this matrices and do a swap. So these are the only two operations I am allowed. So first thing about why it can guarantee us we can actually make our first row equal to the target with 2m total operations. Um, why this budget is only 2m if guarantee the letters we need in this T exist in our matrices? This is the first question I ask myself. I realize in the worst cases, so in the worst cases of your matrices, you have a target and this is your S1. Let's say you want to switch this G into, let's say at these places you have this letter G, and in your target you have the letter L, so you want to switch this G with something L inside the matrices. I ask myself, what's the worst cases? The worst cases is the letter L doesn't actually exist anywhere in the matrices, but it says from the problem statement, guarantee a solution always exists. Then there must be an L exists in this matrix. Now the best case is right next to me, so I can swap directly. Or the best cases is, oh, it's just down somewhere in the same column, then I can swap directly. Then this takes one operation for free. But I have M position to actually fix. In the worst cases, how many steps can each position take? In the best cases, it's 0 step because if the letters already match, then it take me nothing. But if they are not matching, I can find someone in the same row or in the same column that also takes me on one. But what about even worse? I ask myself, well, what about if this L is randomly here, then how would I move? I got two options, right? I got two options, which is if the L exists to the lower left of myself, I got two routes. I either move it up to the first row and then swap to the G. So that's my row one. Or I swap myself to the right first, still in the same row, but make myself in the same column as this G, and then swap it to the top with this G. This is my row two. I ask myself, well, which one do I prefer? Then I realized I must use the row two. Because if I ever use the row one, am I, I'm a stupid human. I like to fix my string from the left to the right. So that basically means I should trust myself everything before the C is fixed. So if I actually followed my route 2, I would interfere with someone I already fixed because I have swapped it with this G. What if this previous places does not want this G? So I quickly realized I should not go into this route 2. Sorry, I should not go into this route 1. but stick with my row 2 strategies anyway. No matter what, I should stick to my row 2 always because it's the safest path. They all take a step size of 2, but this row 2 where I first swap to the right and then swap up with the G will not interfere with any previous letter I have fixed for myself. They're all taking 2 steps, but never interfere with all the previous fixed spot I have taken. Then I realized that's the worst cases. The worst cases is taking 2 steps without interfering any previous answer. I can fix this G in 2 steps. Similarly, if like this G, if this L actually exists somewhere to the lower right of this G, I should always take this black row where I switch left and then I switch up. Um, I don't like going up first and then swap it because what if here it's already a match? Then you kind of ruin the match. So I don't like going into this green route, even though it's another alternative to make it work. But I could possibly delete a match here by swapping with the G. So without interfering any future possible matches or previous existing matches, I should always, if the G, the target letter, is to the lower right, I should always swap it to the left and then swap it up. So that's my strategy. I realized, oh, the best case is 0. I don't need to move at all. The intermediate best is I can find the target letter in the same row, same column that takes me on 1 operation. Now, finally, in the worst cases, I can always fix my mismatch in 2 steps without interfering future matches, without interfering existing matches. So then I realized the budget of 2M is actually a reasonable budget because for every mismatch, the worst cases, I can use 2 steps to fix it. Then in total, there are M spot. Then the worst cases I can use is 2M operations. I can fix all the matches. Now, with answering this question, we actually quickly figure out the strategy to play the game. So whenever you find a mismatch, let's use a for loop to go left to right in your string 1 and compare it with the target. Whenever it's a mismatch, what is my strategy? I just scan linearly for any replacement letter. Scan linearly only to your right. So you have some intermediate G that is mismatch looking for L. You should only search for your right. So for future letters for L, you should not be searching back for your already fixed letters. Even if there is an L exists, swapping this L with this G will actually make your previous fixed letter ruined. So you should not be looking forward. You should always look into the future for the possible L exist. But you are allowed to always look down for the same column for and your target letter, let's say L. So you can actually search horizontally freely. And what is the runtime complexity? For that, so I realized in the worst cases, if you're looking to the future remaining letter for it now, it's all of M. Because every row you can have M letters. Horizontally, this matrix is N times N, so it's all of N. Well, if the word is as great as this, I quickly can figure, well, in the worst case, all of them, it's scanning to the linearly it fixed, then it's all of N times N. Even if it's two words, everyone I look horizontally, it's N times N. And in this question, N that large, I think it's 10 to the power of 3. Oh, I'm very happy. This is 10 to the power of 6. I think in this question is given me for free. And then I quickly realized, well, what about these cases? What if there's no matches in the row and in the columns? Then I basically have to search for all the spaces. I basically need to search for all the letter matrices to actually find my existing letters. So in the worst cases, this add complexity to it. So it's m times I have m letter. What if m every one of the letters in the worst cases I have to scan through all the matrices to find the letters I need to swap to. Now this gives me trouble. This is 10 to the power of 9 or even bigger. Now the problem is, oh, in the third world where this number actually does not exist, how can I look up where my target letter is without scanning through these matrices many, many times? Then I quickly realized, oh, I can use a map. Let's map the character into the places where it exists so I can quickly into the coordinates where it actually exists in the matrices. Then in O1 of time, I can look up where it is without scanning through these matrices again. Then I can get rid of this O times N. Now this time actually meet the requirement. Now here is my code structure planning. There are T test cases, right? Now for every test cases, I should read in the dimension for my matrix, the target string, and then my letter matrices. It's one indexed. I build the location map for the second row till the last row because these are the letters I'm allowed to swap to row one. And these are my target letters if it doesn't exist in the same column, the same row. Now I create a map to map the character into where are the list of coordinates that actually store the characters so I can use without scanning through these matrices. In short, it's going to be Sij, what letter you have is a map, right? And then add its coordinate. Um, and this helper function is to update this map. Because once you have swapped the letters, like if you have swapped the column um, horizontally, then the coordinates actually doesn't exist in these old places. It now exists in these new places. Same thing for the letters, right? So this is a helper function to update whenever you did a horizontal swap, or if you did a vertical swap somewhere not in the first row. Some letters, some previous operation did this swap, and then the location for the letters is going to change. So this is a helper function to help me update this old this ij is removed from some old locations, and then you should add this ij to some new letters to locations. And then this operation is helping me to pre-store the answer, the string of answers I need to print out. Now I go from basically this for loop is what I said. I go from left to right. If the current letter is the same as my target, then I should skip it. Now this is a case when is not the same as my target, then C is the letter I'm basically searching for. Now this priority 1, 2, 3 is corresponding to my gaming strategy. So priority wrong is I searching horizontally. Here the key point is j greater than k. You only to look to the right, so you're only swap the answer to the unseen ones. And then if you find the match, you do a horizontal swap. Here you don't update the map because you're not interfering with the other rows. It's only row one. So you just swap directly. And then priority 2 is you search for the target in the same column. Now, when this column is being swapped, you actually need to update your functions because now see this swap the lower row is receiving a new letter. If this letter is ever being used in the future for somewhere back here, you can use it. So let's update the information and do the swap accordingly. Now finally is if it doesn't exist in the row, or in the columns, then we have this pre-stored map. And then you can do O1 lookout for, oh, where does it exist somewhere else in this map? Now, when they are not the same, we follow the strategy based on where is it located at. Is it in the lower left or up lower right? Then you do the swap and update the positions accordingly. Um, and that's all I want to talk about for the solutions. Any questions? I think this round of question is especially hard for implementation. It's easy to come up with a strategy to, as a human, to give a solution to the problem statement. Implementation wise, it's a little bit hard, especially for the this one, the binary ones. Even if you find the patterns, it's hard to think of how I transform the binary back to the original value, applying the mod rules. The first one I think is just a math problem, but you might miss the point where you should best sort them accordingly and find the corresponding places in the partition group. And that's all for the bronze level. Thank you everyone for coming. 那我就先下喽。好的，拜拜。
Thank you, Stacy. Yeah. If the YouTube audience have any question, please leave your comments on our YouTube channel and then our coach will check it out later. Yes, the silver level will still in the same Zoom. Yeah, thank you. Let's wait for Alvin to come because Alvin just go through the gold level. Hello everyone, welcome to our USACO third contest live solution silver level. Avan come back from the gold level. Let's welcome Avan. I think if some SCAM student, you are pretty familiar with our teacher Avan. Avan is the USACO silver level Grandmaster and Grandmaster programs teacher. So let me hand over to Avan now.
Hello, everyone. Okay,
Yeah, YouTube works. Yeah, good. Avan, we can go ahead.
cool.
Would you mind to share screen first? Yeah, to
Yeah,
all
yeah.
the student.
Give me 1 second.
Sure.
Yeah. Hey, everyone. Yeah. Okay. So yeah, here's a live solution for silver. Um, yeah, this is me. Yeah, I'm currently a PhD student at Purdue. Yeah. And here's a summary of okay, yeah, like the topics of the problems. Or I guess I'll first say yeah, I personally thought this was like a pretty hard silver contest. The problems are super ad hoc. Yeah, they're not easy to solve like very fast. Uh, Personally for me, it took some time to come up with the solutions compared to other silver contests. But yeah, Clash was kind of a problem, like a simulation problem. Like basically, I'll talk about the problems in detail more later, but most of the problem was about like figuring out how to do the simulation faster. Yeah, and then milk buckets. Yeah, I put it under ad hoc slash math. Um, yeah, and then point elimination. Yeah, this is probably the trickiest problem, and at least for me, and the most interesting problem. Yeah, so this is pretty ad hoc. There was some greedy stuff that involved. Yeah, but let's get into the contest. Um, yeah, yeah. So I think problem one. Yeah. So the idea of problem one is like you do a greedy strategy, and then you want to simulate it fast to make it work fast enough. Yeah, let me rearrange these things. Uh, Give me 1 second. Okay, right, great. Um, yeah, but basically the idea for the problem for problem one is uh yeah. So you can just do a greedy, right? So in the case where uh yeah, so the problem says that if there's at least one win condition, then the next card you play must be a win condition, right? Um, so if there's a win condition, we're just gonna be greedy, right? Yeah, pick the cheapest. Yeah, yeah, like the cheapest one. Like basically you have like zero elixir and you just wait until you have enough elixir for the cheapest one and you take that, right? So if there's a win condition, then pick the cheapest one. Otherwise, pick the cheapest non-win, right? Yeah. Uh, yeah. So I think if you just, yeah, if you implement this directly, since T is like, I think the queries are pretty large, so you're not going to get any of the subtasks, but let's just consider this greedy, right? And how to make it faster, right? Um, yeah, so yeah, so yeah, so basically, like one thing you can observe is uh, like let's say you pick, consider like the sequence of things that you pick, right? So maybe you pick A1, or A is already taken, so B1, B2, B3, B4, and then you're going after some point, this greedy strategy is going to keep cycling. Um, and the length. I think you can show the length is like n minus h, but you don't really need to worry about it as long as the length is small. Like you can get your implementation to make this work. But basically the strategy then becomes like like you find this last cycle, right? And then you have this t as an input. And then basically you're going to repeat the cycle many, many times, right? You're going to repeat the cycle, uh, right? And then maybe you'll repeat part of a cycle. And this is the last place, last one, last card where the time is less than or equal to t, right? Yeah, so you're gonna keep drawing cards and you're gonna pay like different amounts of Elixir. And then at some point you're gonna reach a cycle, and then you can just like calculate an O of one, like how many cycles you actually need. And then there's this last part, that's like part of a cycle, right? So that's like a high level idea for how you can like approach this, right? For the actual implementation, yeah, maybe you don't need that much this much, but I just like calculated the first 26 uh yeah, first 26 cards. So you can just imagine there's a list of the first 26 cards, and then consider like the cycle that ends at the last place, right? And then yeah, and then you can also have like a vector of there's not a great straight line. Okay. Yeah, whatever, it's better. I guess not really. Yeah, so you can have a vector of the total wins. So you can think of this as like a prefix sum, right? So like at the ith position, this is the sum of all of the wins, like zeros or ones, until the ith card, right? And then you can also, yeah, so there's just one way to implement it that felt convenient to me. So there's a total wins, a prefix sum, and then this is the total time, prefix sum, right? Um, and based on the first 26 cards, so if the query is like less than 26, then you can just yeah, you can just do the binary search on the time and then find the total wins and you're good. So we care about the case where the time is pretty large, right? So we have the total wins. It's like a prefix sum, like prefix like total wins for the first I cards, and then total time that it takes to get the ith card, right? And then you basically consider the last cycle, right? And then the length of this like the amount of time, the length of the cycle in terms of time is going to be this value minus this value, right? And given this query, that's the time, this will allow you to determine how many cycles there are, right? So you can determine how many full cycles there are. So there's all these full cycles. And then there's also this partial cycle, right? And to actually calculate the length of the partial cycle, you know how much time you have left from here. So you do a binary search over this part. You do a binary search over this part to find like the last card that you're going to draw in that time, right? So you can think of this as whatever you pre-computed plus a bunch of full cycles plus a partial cycle, right? And then to find the total number of wins, then you just take the prefix sum of this and then consider the prefix sum of any cycle, multiply it by the total number of cycles, and then you also have the length of this partial thing. So it's going to be this subarray sum, uh, or like the difference of this value and this value will give you the total number of wins, right? Yeah, any questions? I'll just summarize this. Yeah, so for this problem, there's a greedy strategy. And the main part of the problem is how you simulate it fast. Yeah, and basically you can show that you're going to keep cycling. Yeah, and then you care about like the total number of cycles you make after whatever you pre-computed. So and to do that effectively, it helps to store like the total time for each card that you get, right? And you can use that to calculate the number of full cycles, and then there'll be some partial cycle, and you can binary search over this array to find like how many cards you're going to draw for the partial cycle. And then we can calculate the rest using prefix sums, or using the prefix sum of all the wins. Sorry, I did not read the chat. How do you know when the cycle starts again? Good question. Yeah, so yeah, one way to do that, I think you can show that it's actually n minus h, but like even if you don't show this, like uh just consider the final element of whatever you pre-computed, it's equal to x. Um, and then the element over here is equal to x. Um, I haven't actually tried like proving like when it converges, so I'm actually not sure. But um, yeah, maybe you don't need 1e6. I think the reason I put 1e6 is because n is up to 2e5. Uh, right. Maybe you can prove something. I'm actually not sure, but maybe you can prove that like instead of 1e6, you only need like 5n or something. But based on the fact that some of the inputs are 2e5 and it worked for 1e6, this suggests that it like converges fast enough. But I haven't tried formally proving this part. Yeah, so in some sense you can think of it as proof by AC. Yeah. But yeah, maybe there's also a way to like argue about when it converges. Yeah, so I think like when I was actually doing this problem, I was getting wrong answer. So I was like doubtful that this is actually the right approach. But then I just found some bug, like small bug, and then it worked. Yeah, but I didn't try to think too much about how to actually like prove things for this problem specifically. All right. Okay, let's look at the next problem. Yeah, this problem was kind of interesting. Yeah. So yeah, you basically update the value, like the capacity of a bucket, and then you want to find like yeah, you're given queries to update the value of a bucket and then find the number of things, amount of things in the pool after it's empty, right? So one thing you can observe is that, or like kind of the structure of this, if you put the buckets to like in a column, right? So yeah, let's say these are your buckets. So like this will gradually get filled. And then the next time step, this will dump below to the bucket below, right? And then this will repeat. So it'll get filled again and it'll get dumped below. And then this will get full. So then this gets dumped below. And maybe this gets partially filled, right? But one thing you can observe is that this is kind of like periodic, right? And we'll just look at a few cases, right? So if A of 1 is equal to 3 and A of 2 is equal to 3, sorry, if this is equal to 3, then after like 4 seconds, so this basically has a period of 4 seconds, right? It gets filled and then it empties, right? And then, yeah, so at t equals 4, it empties. And then at t equals 4, this gets filled. And then at t equals 5, it empties. And then basically these will have a period of 4. So it'll empty at t equals 4, 8, 12, and so on. And this one will empty at 5, 9, 13, and so on, right? And you can kind of look at like other cases, right? So if this capacity is 3, sorry, um, yeah, if this capacity is 3, and then this one is like 6, then the period of this, so in order for this to empty, this has to like the 3 has to dump twice into the 6, right? So period, I'll just write it as P subscript 2 is equal to 2 times P subscript 1, right? In general, like we get something like, uh, yeah. So in general, like to find the period of how often they empty, you can get this kind of recurrence. The period of the ith bucket is equal to the ceiling of AI over AI minus 1 times the period of the I minus 1's bucket, right? Right? Um, and the question is asking about like how much is going to end up in the pool, right? And the pool is impacted by whatever the nth bucket does, right? Right. So one thing that we care about is about the period of the nth bucket. But we can just like we can just like keep expanding this. So we get the period of the nth bucket is equal to ceiling of an over an minus 1 times ceiling of an minus 1 over an minus 2 all the way up to the ceiling of um uh sorry, yeah, that's correct. A2 over A1. And then just, yeah, we need to remind ourselves, right? In this case, the top bucket is 3 and the period was 4, right? So it's going to be this times the period of 1, which is A1 plus 1, right? Yeah, I'm going to like rewrite it so it's increasing. Yeah, basically you get, yeah, so you get Pn is equal to A1 times ceiling of A2 over A1 times ceiling of A3 over A2 all the way up to um yeah, an over an minus 1. Yeah, so one thing we're now able to do is we just update the value, and like what if you update a single value, then like if you update AI, it's only going to change like AI is only going to change two values, right? AI over AI minus 1 and then AI plus 1 over AI, right? So we can kind of maintain this product. Um, I guess one caveat is like maybe this bucket is tiny and this one is huge, and this one is tiny, this one is huge. So you might get like 100 times 100 so many times. So this will overflow. But um, like what I claim is if the value is super large, then nothing is going to end up in the pool, right? The period needs to be like very small. It needs to be like reasonably small, like at most 2018, right? So what we can do instead is, yeah, so whenever we update an element, instead of maintaining the product as a number, um, yeah, maybe there's other ways to do it, but what I did was maintain a multiset uh, of the values that are greater than 1, bigger than 1, right? And then one thing you can say is like if the size, so I guess this is roughly 2 to the 60, right? So if the size is like greater than 60, if the size of the multiset is 60, then we can kind of just ignore it, right? Yeah, so now we have like enough information to make updates, and then the period is basically going to be product of the values in a multiset. So multiset basically, oh, I forgot to add the plus 1. Uh, Multiset basically stores whichever values are greater than 1, right? And if the multiset is too big, then that means we're not going to have anything in the pool. The only case we care about is if this multiset is small, right? Yeah, so that's how you calculate the period. Yeah. So to actually answer a query, uh, like you don't just care about the period, right? So you also care about like so the behavior is like the nth bucket is not going to pour for some time, and then it's going to pour for the first time, and then it's going to be periodic, right? So let's just say that EI is like the first time uh, that bucket I pours, right? Um, yeah. Then like the total amount of water in the pool is going to be like uh Yeah, so it's gonna be AI. Wait, so like if the time is less than EI, then it's gonna be 0. If it's greater than EI, then it's gonna be like uh AI plus T minus EI divided by PI times AI, right? Right. This is gonna be the answer to the query. This is the number of times this is the first time that it gets poured. It's gonna pour AI. And then this is the number of times it gets poured after AI. This is based on like the periods, right? So this is going to be the answer to your query. I haven't actually talked about how you calculate EI. Um, the way I came up with it during the contest was like, okay, let me just delete this. Yeah, so basically you have uh if you want the ith bucket to get emptied, right? So like the the first case is like let's just consider they're the same size, right? So if they're the same size, then you'll have EI is equal to, so this bucket gets emptied, this gets filled, and then this gets emptied in the next stage, right? So you'll have EI is equal to EI minus 1 plus 1, right? So if they're the same size, it'll look like that. But if this one is very small, if this one's very small, yeah, then you'll get something a bit more involved, right? So the first time it'll get filled up to here. Yeah, so it's gonna be like at time EI, uh, yeah, at time EI, plus 1, it'll look like this, right? Uh, yeah, yeah, so it's gonna end up being, EI is equal to EI minus 1 plus 1 plus PI minus 1. So after you fill it this up to here, then you need to fill it up to the brim. So the number of times you need to fill up to the brim is going to be AI over AI minus 1, right? And then you can kind of simplify this to like uh, EI minus 1. Since this thing over here is equal to PI, so it's going to be EI minus 1 plus 1 plus PI minus PI minus 1. And then you can simplify this to like, uh, yeah, uh, yeah, yeah, you can show it by induction. Yeah, it takes a bit of work to actually do this in the contest, but you can show it's equal to PI plus I minus 1, right? And you can verify it's true for the first bucket, right? Because the first time it pours, it's equal to the period, right? Yeah, and you can like also verify this true where all the buckets are the same size, right? So the time the second bucket pours is gonna first time the second bucket pours is gonna be like um yeah, the period plus 1, right? Yeah, so you get a formula for the first time that the last bucket gets poured. So yeah, and then basically you can plug it into this, right? Any questions? I'll summarize this in a bit. Yeah, so I think the main observation to make is that like the pouring of the buckets is like periodic, and you can maintain the period, like you can express the period as this product. And when you change a value, only a few terms in the product change. And you only care about the case where the product is small. So you can keep all the values that are greater than 1 in a multiset, and you can kind of like output 0 whenever this multiset is too big, right? Um, yeah, and yeah, and basically you get like PN, like the period of the nth bucket is this, and then the time that the first thing pours from the first bucket is based on this formula, it's going to be En plus n minus 1, right? So you consider the first time something pours from the nth bucket, and then you calculate the number of additional pours that happen from the nth bucket based on the period of the nth bucket. And you can answer each query in O of 1 time. or you can answer this query here in O one time. Of course, for the update, this will take like log n, uh, or log of 10 to the 18 time, because um because you're updating a multiset with up to like 60, which is log 10 to the 18 size, right? Cool. Any questions? Yeah, so the high level idea is like you can think of these buckets as periodic, and you want to reduce it to some math calculations. Yeah, but it takes some work to actually like write, like see the details. But yeah, once you have the period and you can calculate the first time that it pours out, then it becomes like a fairly simple calculation. Okay, let's look at problem 3. Yeah, it's a short statement, but yeah, I thought it was the trickiest problem in the contest. Um, yeah, so there's two kinds of operations. Either you remove two things that are adjacent to each other, or you swap their y coordinates, right? Yeah. So I think like geometrically it looks something like this. So if these are the 2 points, um, I'll just draw them in black. Then in red, what they finally look like will be like this. And then if they're like next to each other like this, or next to each other like this, then that means you can delete them, right? So I claim like looking at it geometrically like this, is not really that, doesn't end up being that useful. But there's like a much nicer way to think about this, right? So you can swap their y coordinates. So just consider like an array of the x's and then an array of the y's, right? So all the operation is doing is it's swapping two of these, right? So one way you can think of it is like you can shuffle this however you want, um, any way you want, right? Because like any shuffle, you can just think of that as swapping, right? A bunch of sequence of swaps, right? So you can kind of think of this problem as you're shuffling both the x's and y's. Um, and then one other thing is like for the deletions, um, yeah, for the deletions, like there's no reason to do them at the beginning. Just like do them all at the end, right? Right. Right. So you can do all the deletions at the end. But what the deletions actually look like is in some cases maybe there's A and A over here, and then B and B plus one, right? In that case, you can like delete these, right? Um, or maybe you'll have like C and C over here, and D plus one. In that case, you can delete this, right? Yeah. So these are the kind of deletions that are allowed, right? So basically they're either equal for x and adjacent for y, or they're adjacent for x and they're equal for y. So one way you can think of it is you have a bunch of equal pairs in x, um, and then you're matching it with adjacent pairs in y, right? And then you're also having equal pairs in y, and you're matching with adjacent pairs in x, right? So I'll just redraw it again like this. So if you group the x's into equal pairs, let's say these are equal pairs. So it's of the form like A1, A1, A2, A2, and so on. And then you also group have a group of the adjacent pairs. So you have A1, A1 plus 1, A2, A2 plus 1, right? Something like this. Um, Basically, you want to match the equal pairs in X with the adjacent pairs in Y. and then match the adjacent pairs in X with the equal pairs in Y, right? So the size of these two things has to be equal. And then the size of these two things has to be equal, right? Yeah. So yeah, so this is like a pretty important thing to observe, right? Yeah, so you can reduce it to you're matching equal pairs from X to adjacent pairs in Y, and then matching adjacent pairs in X with equal pairs in Y, right? Um, yeah. So maybe this motivates some idea like, what if, yeah, I want to find like a bunch of adjacent pairs in X, from the X's and then create a bunch of equal things. Um, Maybe like the number of adjacent pairs lies in some kind of interval, and I can kind of slide things either outward or inwards here, or I can slide the number outwards or inwards here so that they perfectly match, right? So let's try considering like how many adjacent pairs we're allowed to have for the x's, right? So yeah, so that's okay. I'll use the left side of the screen to draw this. Okay, yeah, I'll use the left side to draw this. Yeah. So just let's first of all consider the frequencies. So let's consider the frequencies. Let's just say consider just x's, right? We're just considering like um for the x's we either put the values in some adjacent pair or we put the values in some equal pair, right? So let's consider the frequencies, right? So let's say this x value occurs an even number of times. Next one occurs an even number of times. Let's say this also occurs even number of times. Let's say that this occurs an odd number of times. And then this one occurs even number of times, even number of times, even number of times, odd. Yeah, let's just start with here from now. Or yeah, I'll also do even. Yeah. Then basically, if we consider the number of adjacent pairs, the number of adjacent, so let's just say this is the frequency of 1, 2, uh, it can be anything. Yeah, like 10, 11, 12, 13, 14, 15, 16, 17, 18, right? Basically, like the number of adjacent pairs that include the 10, let's say there's no nines. So number of these pairs has to be even. Because if it's odd, then uh, there will be an odd number left, and you can't make like you can't make the an odd number of things into a bunch of equal pairs. That just won't work, right? So we're just considering the number of adjacent pairs. So there's even number from here, even number from here. Yeah, even here. Since we picked a even number of adjacent pairs that it contained this odd number, then we're on like this pair is only allowed to occur an odd number of times, right? And then now there's an odd number of this thing left. So you have to have an odd number of adjacent pairs for this, and then an odd number of adjacent pairs for 15, 16. And then yeah, for 16, 17, you need an odd number of adjacent pairs. And then for 17, 18, since you took away an odd number of things, there's an even number left. So you need an even number of adjacent pairs, right? So this tells us about the minimum number of adjacent pairs we're allowed to take, right? You can take, yeah, I'll just write in a different color. You can take this pair 0 times, 0 times, 0 times, 1 time, 1 time, 1 time, 1 time, and then 0 times, right? So this is the minimum number of adjacent pairs, right? Right? You're required to take these because there's an odd number of things you have to take. You have to take at least one, right? So after you take these adjacent pairs, now everything becomes even, right? Everything becomes even, right? All the frequencies are even, right? So like you have two choices. One choice is don't take any more adjacent pairs, right? If you don't take any more adjacent pairs, then you just take a bunch of equal pairs for each, right? Yeah, so you just take a bunch of, you just divide it into blocks of length 2, right? right? Otherwise, you could consider taking more adjacent pairs, right? So the strategy here is, yeah, so you can show that it's optimal. Uh, yeah, let's just assume they're all next to each other and they have an even frequency, right? So start from the leftmost. If you want to maximize the number of adjacent pairs you take, first of all, like all these have to occur an even number of times. So they could occur zero if you want, but the greedy strategy is go from left to right, and then at each stage, take as many as possible, right? Uh, yeah. So go from left to right. For the leftmost, take as many as possible. And then for the next one, you take as many as possible again, right? And then this one, you take as many as possible, right? Yeah, and it's actually something you can prove, right? Let's say you don't take, like, let's consider an optimal solution. Uh, and like maybe the adjacent pairs, they took this much out. Um, and then the next, yeah, let's just say the next set of adjacent pairs maybe took these, right? You could have taken more in the beginning, right? And you actually can without hurting your solution, right? You just uh, okay, let me make this tower a little bit lower. Um, yeah, let's say this tower is a bit lower. Yeah, you could have taken more in the beginning, right? You just like to do that, you just delete this, oops, and then you add this over here, right? And it's not going to hurt you, right? It is just going to help you because you have more options later on, right? Yeah, so greedy works when considering the number of pairs you take, right? So what this gives us is an interval from the min number of pairs, uh, min adjacent pairs to max adjacent pairs, right? So you can calculate this for the x's, and then for the y's, you can calculate the min number of equal pairs, and then max equal pairs, right? And one thing you might have noticed is like in this case, you're only allowed to have an even number of adjacent pairs. Like the parity won't change, right? Because you have to take you have to take an odd number. Like the sum of adjacent pairs, the parity is not going to change, right? Even plus even plus even plus odd plus odd plus odd plus odd plus even. That's the parity of the number of adjacent pairs you have to take, right? So there's two things you have to check. One is these intervals intersect. So this is for y and this is for x. So one of the things you have to check is they intersect. And then the other thing you have to check is the parity is the same, right? And as long as that happens, then you're good, right? Any questions? I'll summarize this. Uh, oh, I've actually looked at that problem. I don't think you need 501 for that problem. Or I think that problem was greedy. Yeah. Yeah, I think like, yeah, if you're doing well in the 400 class, then yeah, that should be like, yeah, you should be like strong enough to uh either do that problem or like be able to upsolve it. Yeah, I don't think like 501 is a prereq for that specific problem. Yeah. Yeah. I'll just summarize the solution, right? Um, yeah, so yeah, we kind of reduced this to a problem where we want to match like equal pairs of x to adjacent pairs of y, and then adjacent pairs of x to equal pairs of y by like shuffling the values in x and y. Yeah, and then uh, yeah, so the number of equal like this brings a question of like how many adjacent pairs can we actually have to get a valid matching, right? So looking at the frequencies, this allows us to actually calculate like the number of adjacent pairs we need, right? Yeah, so basically, yeah, so the structure is like the first odd element, you have to have an adjacent pair from there. It's required because it's odd, right? So you can take the minimum number of adjacent pairs, uh, because a bunch of these are required to occur even number of times. Like when you go from left to right, you can deduce this. And then a bunch of the adjacent pairs, they're required to happen an odd number of times, right? Um, yeah, so you can pre-place like you can just take one for whatever needs to happen an odd number of times, and this gives you the minimum number of adjacent pairs that you need, right? And then after that, all the frequencies are even. So you go from left to right and greedy to find the largest number of adjacent pairs, right? Um, yeah, yeah, and then the solution ends up being like, uh, as long as you can get some number of adjacent pairs from the x's that equals the number of equal pairs from the y's, then you're good. Right? Yeah, I'll also show my implementation. It's actually pretty short. Uh, yeah, yeah. I think for this contest, yeah, the problems are pretty hard in the sense that like it takes a while to come up with the observations, but the implementations are actually like pretty short just for this contest. Yeah, I wouldn't say the same for the other silver contests. Yeah, but uh, yeah, um, yeah, but my implementation for this one specifically is pretty short. Um, yeah, I'll share that. Uh, yeah, so for USACO, I guess you're not allowed to have pre-written code or templates. So I usually just type this in the beginning of the contest because that's, I guess it's a personal preference. Yeah, I think most people don't do this. Yeah, maybe in some ways it's not recommended, but this is what I'm comfortable with. Yeah. Uh, but basically the idea is I have the frequencies of x's and frequencies of y's. And then I find the minimum and maximum number of adjacent pairs for x and minimum maximum for y. There are some cases where like the input is like has no solution, right? But like assume it has a solution, right? So the algorithm is just what I talked about, right? Yeah, so since the values are up to 1e18, like the frequencies can be sparse. So you need to use something like a map, right? But basically what this algorithm does is it was, as I explained earlier, um, it takes the adjacent pairs that are required to have happen an odd number of times. That gives you the minimum. Um, and then it tries to maximize the number of adjacent pairs such that a solution still exists by going from left to right, right? So I get the range for x and then the range for y, right? Yeah, and then yeah, since we care about mapping adjacent pairs in x to equal pairs in y, then you can just like the number of equal pairs is equal to n over 2 minus the number of adjacent pairs. Yeah. So you get the intervals for x, the adjacent pairs, and then the interval for y, the equal pairs. And then basically you need to check that they intersect and then that they have the same parity. Right. Yeah. Any other questions? Let me just see if I have any comments about the other ones. None in particular, but yeah. Cool. Yeah, I'll stay here for some time if any of you has any questions about this contest or silver in general or anything.
Yes, because the time delay, so we can wait a few more minutes for the YouTube audience. Thanks, Alvin.
Yeah. Sure, I can go over that. Yeah. 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 Yeah, so basically like the goal is to find the minimum number of adjacent pairs of the form X is already taken, but A and A plus 1 so that the frequencies of everything is still even, right? Because if the frequency of everything is even, right, then you don't even need any adjacent pairs. You can just make all equal pairs, right? Right. Um, but yeah, let's consider the frequencies of frequencies of all the x values, right? So let's say that we can just like pretend it's like 10, 11, 12, whatever. Let's say there's even, odd, even. So this is the leftmost thing that occurs, like the non-zero number of times. Odd, even, odd, even. Yeah, so there's some cases where it's not possible, like there's three odds or something, but I'll just consider this. Wait, this should work, I think, surely. Yeah. So what this tells you is the number of adjacent pairs that have 10 and 11, it has to be even, right? Because if it's odd, then this will end up being odd, and we can't divide the odd into a bunch of equal pairs, right? So this has to be even. And then since we took an even number from this one, it's still even. So the number of adjacent pairs over here has to be even, right? So the number remaining for this one, 12, is like the initial odd number minus an even number. So this is an odd number now. So we have to have an odd number of pairs, right? And since we took an odd number of pairs here, then this number is now odd. So we have to take an odd number of pairs, right? This number is now even, so we have to take an even number of pairs. And this number is oh, okay, I think I need, yeah, I think it's fine. Yeah. Yeah, and then this is even, so we need to take an even number of pairs. This is now odd because it's odd minus even. So we need an odd number of pairs, right? Um, yeah, yeah, and yeah, that's how you argue like you have different types of pairs where the first element is A and the second one is A plus 1. And you can like go from left and right to figure out whether you can conclude that you either need an even number of these pairs or an odd number of pairs, right? And the key thing is if you need an odd number of pairs, that means that you need at least one, right? You can't take zero because it has to be odd, right? So then the minimum number of pairs, you get that by taking this one, uh, yeah, and this one, right? And once you've taken them, then the frequencies will now all become even. Right. So the thing here is, uh, yeah, I took the minimum number of pairs. I was forced to take these because they're all odd. So the minimum number of pairs is equal to 3 in this case, right? Yeah, and then to find the maximum, you can greedily go from left to right, and then try to take as large of an even number of pairs as you can from each thing, right? Yeah. Yeah, I think when I did the problem, I think uh yeah, I was able to like kind of quickly find what's the minimum number of pairs, but yeah, it took me a while to convince myself that you can just go to maximize it, you can go left to right and do things greedily. Yeah. Yep. Um, okay. Oh, your question about the first problem. Uh, yeah. So I think for the first problem, yeah. I think the 1e6 thing, I scrolled too much. Um, the 1e6 thing that I did was probably unnecessary. Um, yeah, I think you can just like I guess the structure is like there's this stuff that you have access to and there's stuff in the queue. So I guess you can like simulate it until the next time your queue reaches the same state, uh, or something like that. Um, yeah, yeah. Surely, I think you probably, or I think you can prove that eventually the cycle length will be n minus h. So, I would expect that like if you have two cycles of lengths n minus h that have the same sequence, um, if you have two cycles of length n minus h that have the same sequence, um, three to be safe, uh, th- then you can conclude that's your cycle. Yeah, good question. Um, so I'll first say that like I did for this contest specifically, it took me like exceptionally long to actually like come up with the observations. Uh, but yeah, I think like some strategies is um so I think like for this one, I guess like it's not I guess it's like more straightforward. Like if you think of the greedy and how to simulate it fast. This problem is probably like more straightforward in that sense. Um, and then I think problem two, so I think when I did the contest, I like skipped it and tried focusing on problem three, and that ended up being a mistake. Um, problem two, like I think it's like doable to like at least like looking at the sample cases, like sample explanations, like it has this periodic structure. So to at least conclude that there's some kind of periodic structure. So then, yeah, I think, yeah, for problem two, I think also like one challenge is like reading the problem and understanding how it works. Because it took me a while. I think like if you pour a bucket, if this is upside down, uh, something, or sorry, not if it's upside down, but like it's kind of unintuitive in some ways. Like if you pour this down into this and then this overflows. I would expect it to like fall into the pool, but that's like not what the question is asking at all. Um, yeah. So I think like reading this is also like kind of uh a big hurdle. Um, Yeah, but I think like looking at the sample cases suggests that there's some kind of pattern. Um, and this kind of suggests like trying to uh like think about how often each bucket flips. I guess you care about how often the nth bucket flips, right? Um, and I think like this kind of train of thought led me to eventually um like think if these buckets are the same size, then the periods are the same. If this one is bigger, then the period is still the same. If this is smaller, then the period is roughly like this divided by this times the original period, right? Um, yeah, I think yeah. Um, yeah. So I think like the first problem and second problem, they're like things you can train by just doing a lot of problems. Yeah, because first problem is kind of standard, like it's like simulating something and you want to do it faster. Um, and like being able to do the first problem like, comes more from experience than from like observations, I think. Um, yeah. Um, yeah. Uh, and then the second problem, like after you realize it's a product of a bunch of things, then like you can realize like you can maintain the product. Yeah. I think the third problem is the hardest, right? Yeah. Um, like I think I was fairly quickly able to observe that you want to match like A and A with A and A plus one, and basically from X and then Y, you want the equal things to be matched with adjacent, and then adjacent to be matched with equal. But I honestly was stuck on for a long time how to do this. Um, yeah. Uh, but yeah, yeah. Uh, yeah, I think like coming up with observations, like a lot of it comes from practice. Um, I guess like yeah, I think like it, I guess we're almost done, but like in contests like code forces, like those kind of those kind of have more emphasis, maybe more emphasis than USACO on like coming up with observations quickly, since those contests are like USACO is 4 hours, but code force is like 2.5 hours. So you get rewarded for like being able to do problems faster. So I think that is like a useful way to train observation skills. Like code force is an ad coder. Yeah. Also like gaining rating can be fun. Yeah. Yeah. Okay.
Thank you, everyone. Yeah, last to notice, we have some upcoming contests from the local high school, like Hacker, the Gun High, and from the Berkeley and Calico from Stanford. So, student, please notice our newsletter or email on our website. Yeah, just team up and have fun with your teammates and classmates. Thank you so much, and thank you, Alvin, again. Good night, everyone.
Right. Thank you.
Thank you, Alvin. By the way, Alvin, could you
Yeah.
mind to share the Go level recordings with me?
Sure.
Yeah,
I'll share that.
because one student told me there are a lot of good questions from the QA part. Yeah, so we would like to cut it. Yeah,
Oh, for gold? Okay.
yeah.
Yeah, yeah,
A
yeah.
lot of students ask the general Go question, right?
Yeah. Yeah.
Yeah, yeah, yeah. Sure, sure, sure. I'm so glad you support us both the silver and gold level. Yeah, thank you.
Okay.
Good night.
Good night.